Today I will provide a video of the playlist Waves and Oscillation. As the name of this playlist, which is Waves and Oscillation, indicates that it will contain the videos on two concepts. First one is oscillations and another is wave. In fact, till now I have provided more than 24 of videos on the concept of oscillations. And the concept of oscillations, in accordance with your syllabus, is almost completed now. So now I will provide the videos on wave motion. Okay, wave aspect will be discussed now in the today's video and also in the forthcoming videos. Okay, but before this first video on wave motion, I have already provided the mathematical aspect of wave. That is what is the classical wave equation, how it can be solved. Such videos I have already provided and uploaded in this playlist, and so you can watch that. Actually, when you talk about wave or wave motion, then in fact, in case of mechanical wave, that is the wave which travels in a medium. Our present aim in this chapter, Waves and Oscillation, is to discuss the mechanical waves only. And that mechanical wave may be a transverse wave or a longitudinal wave. The wave is called transverse when actually the particles of the medium oscillate in a direction just perpendicular to the direction of propagation of wave. But if the particle oscillates on the line of motion of the wave, that is called longitudinal. So definitely in case of mechanical wave, the particles oscillation plays a very important role in wave motion. But there is a confusing fact here. Some students or some people gets confused during the study of wave motion. When you say that a wave is traveling through a medium, actually the particles of the medium oscillate or vibrate about its equilibrium position. But it does not progress through the wave. Wave travels from one region to another, but the particles do not travel from one region to another, but it only oscillate or vibrate about its equilibrium position. Okay. So what actually travels in case of wave motion? That is actually the phase relationship or between the crests in case of transverse wave or compression or rarefaction pulses that appears as a wave. Okay. In fact, in this first lecture on this wave motion, our aim is to discuss a very important wave which is called traveling wave, okay, or progressive wave. If a wave, that traveling wave may be a transverse wave or it may be a longitudinal wave, okay. But if it continues to move in a medium of infinite dimension, and its energy is distributed in a very long region, not in a limited region, then that is called a progressive wave. Particularly in this progressive wave, we are going to discuss the plane progressive wave. When you say plane progressive wave, you may also call it sinusoidal progressive wave. That is a wave whose equation will be expressed either in terms of the exponential function e to the power I omega t minus kx or plus kx, or sin omega t minus kx plus kx. In fact, any function of x and t which is in the form of ax plus minus bt, then this function represents a progressive wave. The function of x and t, where x is the position coordinate or space coordinate and t is time coordinate, and a and b in this expression are constant. So if f of xt is in this form, ax plus minus bt, or you can say that this is a function of ax plus minus bt, ax plus minus bt, then such a function actually represents a progressive wave. Okay? And what are the different characteristics of this progressive wave, how it is generated, all these things we will learn. Now for understanding this idea, let us consider you disturb the medium by some means, and when a medium gets disturbed, a wave is generated. And what type of wave will be generated, that depends on the nature of the disturbance. How you perturb the medium, how you disturb the medium, that actually determines the nature of the wave. So now let us consider that our medium is one-dimensional. Medium is one-dimensional, and here at this point O, which is x equal to 0, we disturb the particles of the medium lying at x equal to 0. Okay? And what is our manner? We disturb this particle in harmonic manner, or let us say, you provide a simple harmonic motion to this particle located at x equal to 0, so that this particle starts oscillating in a direction perpendicular to this x-axis. It means you are providing a transverse oscillation to this particle. Okay? Now, once you disturb this particle, the particle continue to be oscillating about this equilibrium position O, but the disturbance travels in this x direction, which is actually called the traveling wave. Now, if the disturbance produced by U is of simple harmonic nature, then this wave will be described by an equation which will be in terms of sine function or cosine function, and that's why it is also called a sinusoidal wave, or sinusoidal progressive wave, or plane progressive wave. Okay? So for understanding the idea of this plane progressive wave and what will be its equation, let us see the concept of plane waves only which travel in one direction, that is in x direction. And let us take a plane perpendicular to the direction of wave propagation. This straight line which is perpendicular to this x, this don't think that this is a straight line, but this represents a plane A. Okay? Now, in that plane, all the particles have the same phase during oscillation. Okay? But in the next plane of the phase of particle oscillation is different. Okay? Actually, in formulating such a wave motion in mathematical terms, we shall have to relate the phase difference between the particles' oscillations at any two planes to their physical separation in space. Actually, that relation is called the wave equation. And how we can find it, let us see. Let us consider there is a large number of particles lying on this straight line, or you may take a string lying along this straight line. And one of the ends of that string, or you can say one of the particle which we have assumed earlier, is at O, and we disturb this particle in such a manner that it starts performing simple harmonic motion about this O in a direction perpendicular to this x-axis. We consider it. Okay? In this condition, the disturbance produced will move along this medium in x direction, let us say with velocity v. Now, one thing you should remember, that if the medium is isotropic and homogeneous, then this disturbance will travel with a constant velocity. Okay? Now actually you can see if the vibration is transverse, this point, let us say P1 is a crest, this is also a crest, this is a trough. Okay? And to obtain the wave equation for one-dimensional plane waves, let us consider that the harmonic wave traveling in the medium is traveling in this medium with a velocity v, and we consider two planes. One is A and another is B, and A and B are separated by a distance x. Okay. Now let us assume that we create a wave at this point x equal to 0. It means the point x equal to 0 is disturbed at any time t. Okay, and this disturbance traveled down in x direction. Okay, and the particles at this plane A start vibrating in a simple harmonic manner in a direction perpendicular to this x direction. Okay, let us consider that A is the amplitude of that simple harmonic motion of the particle, and t is its time period, and omega is its angular frequency. Okay. Now, if I will ask you to write down the equation of motion of that particle which is executing simple harmonically, you know, if you consider that this psi of xt is the, not xt but psi of 0t, because x is 0 here. This psi of 0t is the displacement of the particle at any moment t. Let us say this is its displacement, this is psi at any time t. Then you know that this will be given by A sine omega t. Or you may write cos function too, or equivalently you may write A sine 2 pi over t time t. Here omega is the angular frequency which is 2 pi over t, where t is the time period of this oscillation. But particle is oscillating about O, but the wave travels in x direction. Okay, so the disturbance passes. Now let us consider that there is another plane B which is separated by plane A by a distance x. Now can you say what will be the time taken by the disturbance produced at this point x equal to 0 or at plane A to reach to the point to the plane B, or x equal to x? It is easy to say. Since when the wave will move from this plane A to B, the distance covered by it is x, and it is moving with velocity v, which is constant. Since we assume that our medium is isotropic and homogeneous, so the velocity of this wave v will be constant. So what will be the time taken by this wave in traveling from x equal to 0 to x equal to x? Here this point is x equal to x. This will be simply distance divided by speed, that is x by v. So the disturbance created at this point O will travel to the position x equal to x in a time x by v. okay, in a time x by v. Now, we now ask the question, what is the displacement psi of xt of the particles located at this point x equal to x and t equal to t? It means at position x and time t, what is this displacement psi of xt? Can you say? Actually, to obtain the answer to this question, you can say that the displacement or disturbance which was created at this point O, that actually travels to this point, and medium is isotropic. So, the displacement of the particle at x equal to 0, okay, and at a time t star. What is this t star? I will talk after some time. This will be equal to psi of xt. What does it mean? Let us see. If you consider that the disturbance is at time t at this position x, can you say when this was at the position x barabar 0? You can easily say, since the disturbance takes time x by v in moving from x barabar 0 to x equal to x, so if it is at this position x at time t, then it was at x equal to 0 x by v earlier. So at this position x equal to 0, the disturbance was at a time t star, which will be equal to t minus x by v. Have you understand? The disturbance which is at time t at this position x equal to x, that was created at a time t minus x by v at the position x equal to 0. So, the displacement of the particle at x equal to 0 and at time t star, which is this much, and displacement of the particle at x equal to x and time t, both will be equal. So you can see I have mentioned all these things here, that psi of 0t, here x is 0, that will be a sine omega t, and instead of omega you can write 2 pi by t. Okay. Now, as I have told you just now, that consider the motion of the particle located at B at a distance x from A. The wave created at A will reach to B in a time x by v, and the wave pulse which is at B at time t was created at x equal to 0 at a time t star, which will be equal to t minus x by v. Since the medium is isotropic and homogeneous, so the shape of the pulse will also not get distorted, and therefore displacement of a particle at position x and time t, that must be equal to displacement of the particle at position x equal to 0 but time t star, which is actually t minus x by v. Okay. Now symbolically, the displacement at x equal to x and t equal to t is denoted by the symbol psi of xt, and displacement at x equal to 0 and time t star, this will be denoted by this symbol. But you know, t star is t minus x by v. But as you have seen that psi of 0 comma t is given by this relation, which is just equation of SHM. So using that very equation, you can say that psi of 0 t star, this will be given by a sine omega t star, but t star is t minus x by v. Okay. So psi of xt is given as a times sine omega t minus omega over v times x. When I have taught you the motion, the continuous media, then several times we have seen that this omega over V was denoted by the symbol K. And always I have told you that this K is a constant in that condition. But when we will study wave motion, then it is called wave vector or wave number. So let us denote this omega over V by K. Okay? And therefore psi of xt is equal to A sine omega t minus kx. Actually, this equation which we have obtained is the sinusoidal one-dimensional progressive waves equation. This equation actually represents a sinusoidal wave traveling in positive x direction. Okay? If this may be like kx minus omega t. In some author like to writing this equation, they prefer in this manner the argument of sine function as kx minus omega t. You may write. Okay. Since this is the wave equation in terms of the sine function, it may be in terms of cosine function, or we also may write in this manner: y equal to a e to the power I omega t minus kx. Because you know e to the power I omega t minus kx, its real part is cos of omega t minus kx and imaginary part will be sine of omega t. So this equation also represents a plane progressive wave. This is a plane wave, one-dimensional plane progressive wave. Okay. So this is the basic equation for a plane progressive wave, and I have told you that instead not y, but you should write psi, and you should write you may write psi equal to a cosine of omega t minus kx, because you know the equation of SHM may be written in terms of this exponential function and this cosine function. Okay. Now, after getting this basic equation of a sinusoidal one-dimensional progressive wave, now let us see some of the remarkable facts contained in this equation. Okay, we will actually discuss now all those things. First of all, when you have derived this result, I have told you that actually the derivation or the deduction of this equation is based on two assumptions. First assumption is the amplitude A of the particle's oscillation does not change with position and time. It means at all positions, at all time, this amplitude remains constant. Okay. So A is not a function of space and time, x and t. Okay. And as I have told you that since we consider the medium as homogeneous and isotropic, so this V is also constant. Everywhere velocity of the wave will be same. But if the medium will be not homogeneous and isotropic, definitely this V will change. But we are talking about the homogeneous and isotropic medium. Okay. Now, this equation, as I have told you, that this equation represents a wave traveling in positive x direction. Now, if you want to write the corresponding equation for a wave traveling in negative x direction, then simply there will be plus sign before this k. It means in this case, V will be treated as minus V. And you know, k is equal to omega over V. So when you will take V minus V instead of V, this will become plus. So psi of xt equal to A sine omega t plus kx. Actually, this denotes the equation of a sinusoidal progressive wave traveling in negative x direction. So in general you can say that a plane progressive sinusoidal wave is represented in general by the equation psi of xt equal to a sine omega t minus plus kx. Here minus sign represents the wave traveling in positive x direction and plus sign the wave traveling in negative x direction. Okay. Now see this function psi of xt which we have written here for displacement. Actually in general this function psi which is a function of space and time you can see. This is in general called the wave function. Actually wave function is the quantity or parameter which characterize the wave, or the wave equation is written in terms of a function that is called wave function. Okay. In fact wave function must be a function of space and time. Although it is a misconception that any function of space and time will be a wave function, answer is no. All functions of space and time can't be a wave function. It will be a wave function only when it varies periodically with space and time. Then it will be a wave function. Or in other words you can say when this function psi will satisfy the classical wave equation, then it will be called a valid wave function. Okay. In fact for this psi is a particular quantity for a particular wave, and for different wave function is different. We will later on study about the sound wave, and when you will study sound wave you will see that when sound wave travels through a medium, the pressure of the medium varies in fact periodic manner with position and time. And so psi of xt has a meaning P of xt in case of sound wave. In case of sound wave, this excess pressure is the appropriate wave function. In the similar manner, when you will study about the electromagnetic wave, you will see that in that case, electric field vector E and magnetic field vector B varies periodically with space and time. So, in case of electromagnetic wave, the role of psi is played by E or B, and so E and B are the wave function in case of electromagnetic wave. If you are talking about the wave traveling on a string, then psi is denoted by y, and this y is actually the displacement of a segment or a particle of the spring. Here in this present discussion too, we have considered that psi is displacement. But for different type of waves, psi has different meaning. But in general, it is a wave function. Okay. Now, as you are telling that this is the equation of a traveling wave, sinusoidal traveling wave. So, we must check that it is a valid wave equation or not. And as I have told you earlier when I have discussed the classical wave equation, that any equation which will satisfy the classical wave equation, that will represent a wave. So if this equation is a valid wave equation, it must satisfy the classical wave equation. So let us try to show this. You know, psi of xt, this is given by a sine omega t minus plus kx. Now find the second order derivative of this psi with respect to t partially, because you can see psi is a function of two independent variables x and t. So definitely if you want to differentiate it with respect to t, you must keep x as constant, and so we have to find the partial derivative. So del psi by del t, this will, you can see this will be omega a cosine of omega t minus plus kx, and therefore del 2 psi by del t square will be minus omega square times a sine omega t minus plus kx. Now in the similar manner you can find the second order partial derivative of psi with respect to x, and that will be equal to this much. This is minus k square a sine of omega t minus plus k. Now let us divide this del 2 psi by del t square by del 2 psi by del x square. You can see this a sine omega t minus plus kx. This is a common factor. So that will cancel out, a will also cancel out, and only you will have omega square over k square. And therefore, del 2 psi by del t square will be equal to v square times del 2 psi by del x square, where v square has been written instead of omega square over k square, or you can say that v is written for omega by k. And after seeing this equation 7, can you say what is this equation? I have already taught you about the classical wave equation and its solution. So definitely you can say that this is the classical wave equation or the D'Alembert wave equation in one dimension. And therefore you can say that this equation definitely represents a one-dimensional wave, and such a wave is called plane progressive wave or the sinusoidal progressive wave. Okay. Now actually in different physical problem we use the different form of this wave equation. You know, the basic wave equation for the plane progressive wave is psi equal to a sine omega t minus kx. Now let us cast this equation in different form. If you take here omega as a common factor, the remaining term will be t minus k over omega times x. Okay. And as you know that omega over k is equal to v. So k over omega, that will be equal to 1 over v. So psi of xt can be written as 8 times sine omega times t minus x by v. This is another important form of this wave equation. Okay. Now again you know that this omega, which represents the angular or cyclic frequency of the wave, this is 2 pi over t, where t is the time period. So instead of omega, now write 2 pi over t in this equation. And when you will multiply the bracketed term by 1 over t, this equation becomes a sine 2 pi t over t minus x over vt. But velocity of the wave times its time multiplied by its time period, this is equal to lambda, which is called wavelength of the wave. Okay, because this is v over nu, t is equal to 1 over frequency, and this is called wavelength. So in terms of wavelength and time period, you may write this equation for sinusoidal wave as psi of xt equal to a sine 2 pi t over t minus x over lambda. So these are the different form of the equation of plane progressive wave. Now as you know, when the wave travels, then particles of the medium varies in simple harmonic manner. Because we are talking about the harmonic wave. Okay. So now you can, and psi of xt, this is actually the displacement of our particle at any time t at position x equal to x. So if you want to find the velocity of the particle, which I have denoted by the symbol u, because here wave velocity has been denoted by the symbol v, then u at position x and time t will be defined by del psi by del t. Here partial derivative again has been taken, because you know psi is not only a function of t, but it is also a function of x. So we must take partial derivative. And therefore a is constant, and when you will substitute the value of psi, this will be a sine omega t minus kx. A is outside of the differential operator, and this sine function will be differentiated. And after differentiation, you get at any time t the velocity of particle, which is called particle velocity. This is u of xt equal to omega a times this much. You can see this particle velocity depends on both space and time. So at same time at different position, particle velocity will be different. And at same position at different time, particle velocity will be different. Now, when I have discussed the problems of continuous media, several times I have talked about the volumetric strain. And you have seen that actually this del psi by del x, when you take the partial derivative of displacement with respect to x, then you get the strain. You can remember, I have provided this idea in my previous video. So, when the wave travels in a medium, the medium gets strained. And what is the strain developed in that medium? That can be found by del psi by del x. Actually, this is gradient of the waveform, and this is equal to minus Ka times cosine of this much. When you will put psi equal to a sin omega t minus kx and you differentiate it, your result will be like this. Okay. And here is u, here is s, h is a strain. So when you will divide this u by s, you can see these two results. This a times cosine of omega t minus kx will cancel out, and the remaining factor is minus omega over k. But omega over k, you know, this is v, which is called phase velocity or wave velocity. So u is equal to minus v times s. It is a most important result which relates actually the wave velocity and the particle velocity. So you can see particle velocity is equal to minus wave velocity times volumetric strain. When you will multiply the wave velocity by the volume strain with negative sign, then you will get particle velocity. This is a most important result. Okay. Now I have actually used this term v, which is called phase velocity or wave velocity, several times, because I hope you have an idea of it. But now let us discuss something about this wave velocity or phase velocity, because this is a most important concept. So I would like to explain it. In fact, it must be clearly understood that the individual particles which make up the medium do not progress through the medium with the wave. They merely oscillate either in transverse manner or in longitudinal manner about their equilibrium position, as I have told you earlier. Okay. Actually, it is the phase relationships which we observe as waves. That is observed as waves. Therefore, the wave velocity, which is also called the phase velocity, okay, it is the velocity with which planes of equal phase, that is crests or troughs in case of transverse wave, and compression and rarefaction in case of longitudinal wave, travel through the medium. Okay, so this phase velocity of a wave is given by this formula, v equal to nu lambda. Definitely you have studied it in your lower classes, v equal to nu lambda. Now if you multiply this equation by 2 pi and also divide it by 2 pi, your result will be 2 pi nu times lambda over 2 pi. But you know 2 pi nu is omega, and k, which is wave vector, that is 2 pi by lambda. So lambda by 2 pi will be 1 by k. So v is equal to omega by k. Okay. And already you have assumed this thing earlier. Now the same fact, same result can be derived in another method, another technique. because you know the total phase, which is actually phi of xt of the total phase of a harmonic wave is actually defined as the argument of the sine or cosine function. When you write the equation psi equal to a sine omega t minus kx, this omega t minus kx, which is the argument of this sine function, that is actually called the phase of the wave. Okay, that is called phase, or kx minus omega t. Okay, so you can say that the phase of the wave traveling in positive x direction is given by omega t minus kx. Okay, now you can see this phase is actually a function of position and time. Okay, so at a given space point, it means x has a particular value, x is fixed. It will vary with time t. If x is constant, you are talking about a particular position, then it will change with t. And see this result. When t will increase, this phase will increase linearly. If you will plot this phase in against of time t, keeping x equal to constant, then when t is 0, the phase will be minus kx. Okay, so this will be the graphical plot. Okay, at t equal to 0, its value will be equal to minus kx. Here x has a constant value. So when we talk about a particular position, then with increase in time, phase increases linearly due to this term omega t. Now, if you now keep t equal to constant, it means we talk about different position for different value of x, but at the same time, then you can see with increase in x, phi will decrease because here there is minus sign. But that decrement will be also linear. So you can say at a given time, with increase in x, phase of the wave decreases linearly, and at a given position with increase in time, phase of the wave increases linearly. Okay. Actually, the decrease in phase is due to the fact that at greater x, the phase corresponds to waves emitted at earlier times. That's why the phase decreases. Let us now know to calculate the velocity with which a wave crest or a wave trough or a compression pulse or a rarefaction pulse, okay, travels. With what velocity it will travel, that is actually the phase velocity or wave velocity. So now let us consider that at x equal to x, there is a crest at time t, and this actually moves to this position where x is x plus dx at time t plus dt. So you can say that this crest has moved by a distance dx in time dt. So what is the velocity with which this crest is moving? That will be dx by dt. Actually, this dx by dt is wave velocity. The velocity with which crest is moving, the velocity with trough is moving, the velocity with which the compression or rarefaction is moving, that is actually called the wave velocity. Okay. So, but in course of motion, this phase remains constant. Okay, and if phase phi of xt remains constant, then its change, or you can say its differential, must be equal to 0. So taking this idea under account, you can now see we can easily find the expression for wave velocity or phase velocity. Phi of xt is constant, so d phi will be 0. Now phi, you can see, is a function of two independent variables x and t. So when you will find its differential change, you must follow the rule of partial differentiation. So d phi will be equal to del phi by del t times dt plus del phi by del x times dx, and that will be equal to 0. But see, phi of xt equal to omega t minus kx. So from this result, what will be del phi by del t? This will be simply omega, because in that condition we have to keep this x constant. And this del phi by del x, this will be equal to simply minus k. So this result is omega dt minus k dx, and that equal to 0. So omega dt is k dx and dx by dt is omega by k. But as we have seen here, that actually this dx by dt, this is actually the wave velocity, because x represents the displacement of the wave. Okay. So these are some basic facts regarding the sinusoidal wave, and this was just an elementary lecture. But in forthcoming video, we will see actual concept of this wave motion. Okay. But again, I am telling you, watch my previous videos on wave equation and its solution. Okay. Thank you very much.